Hi, so it's my great pleasure to introduce Professor Alena Pirutka from Criterion Institute at NYU. The title of her talk is Irrationality Problems.
Thank you, and thanks for the invitation. It's a big pleasure to be here. So my talk will be around some irrationality problems with connections to algebraic geometry and geometry and topology. So here is a plan. In the beginning, I will just introduce some classical properties and examples, properties related to the rationality. And then I'll discuss two more recent developments, one on stable rationality problems, and related to this, the problem of deformation of rationality. So we'll start with very basic definitions. So rationality in mathematics versus social sciences. So what we mean by rationality here, we also fix a field and a projective integral variety. So in Kaczor-Bykar's talk, we already had this definition of being birational. So X is rational if it is birational to Pn. I also put that from the point of view of fields, this means that the function field of X is a purely transcendental extension of the base field. But we are not going to use this second property. Okay, so then one introduces stable rationality. So it holds if X cross Pm for some m is rational. And then there is a unirationality. X is unirational if there is a dominant rational map from some projective space to X. And finally, I put one more geometric property for simplicity over the field of complex numbers. X is rationally connected if any two general points could be joined by a rational curve. So this property, we can view it as an analog of path connectedness. So the interval here is represented by a projective line. So let's see when we can decide when this property holds. So first, from the definitions, we have implications, as well as here. Okay. And in small dimensions over C, so for dimension 1, these notions are all equivalent, and this means that X is birational, just is isomorphic to a projective line. Or for surfaces, they are all in the birational class of P2. So in this talk, we will be not working with varieties of general type, but it's really on another side of these birationality questions. So now we'll have some typical examples and counterexamples. So let me start with one. So consider X a quadric. So define it by some equation of degree 2, quadratic form. And X is smooth. And I will assume that it has a point. Okay, so here is X. And here is my point. So I claim that X is rational. And so what I'm going to do, I'm going to look at lines L containing this point. So through point P. So then what I can do with the line, I can just consider the second intersection point with the quadric. Because the equation is 2, I will have exactly 2 intersection points. Okay, so this defines a rational map to X. And to the other side, if I have a point, then I can also consider the line through P and Q. So those maps are birational. And define it for all lines that are non-tangent to X. And so the space of lines through point in the projective space is just Pn minus 1. And so this shows that the quadric with a point is rational. So let me summarize more examples. So we will fix for what follows a notation. So xd will denote a hypersurface of degree d. So this one is given just by one equation, homogeneous equation of degree d. I do not assume that it is smooth a priori. So indeed, for smooth quadrics with a point, as we've just seen, the quadrics are rational. So for unirationality, there is, for example, a result of color. Smooth cubics with points are also they are unirational. So in those two examples, the rationality and the unirationality are established via some explicit geometric constructions. And so it's actually difficult to establish that something is unirational or rational unless you find something explicit coming from geometry. Also, for rational connectedness, there is a result by Kohler, Miyaoka, and Mori, and independently by Campana, saying that the smooth Fana varieties over C are rationally connected. So in particular, here we find hypersurfaces of degree D with D at most n. So what's special about this result? Maybe you can help me. I'm sure some people know what I mean here. Okay, so no guesses. So I tried to have some relations with the anniversary conference of the Journal of Differential Geometry. So the paper of Kohler, Miyaoka, and Mori was published in 1902, Journal of Differential Geometry, volume 36. And it's even in the selected works, volume 2. So I guess those books are available just at the entrance to this room. Okay. So now let me give some examples over non-closed fields, so probably over reals. Well, as everybody knows, a real conic does not necessarily have a point. So there is one without a point, and in particular, it's not rational. Also, coming back to Segre, there are examples of non-rational cubic surfaces over the reals. So let me explain this one in more details. So I'm going to consider the following cubic that I'm going to call Y for in the beginning. So Y in so surface is 3 over R. So I'll first consider the one defined by the following form that I'm going to call phi. So x squared plus y squared, v plus u, u minus v, u plus v, equals to 0. So it's a cubic in a projective space with homogeneous coordinates x, y, v, u. Okay, then let's see if this one is smooth. Actually, the singular locus, if you compute what it is, then you find that u equals to v equals to 0, and x squared plus y squared equals to 0. Okay, this could happen. But what it means that those singular locus has no real points. So why the real points, they are actually all smooth. Okay. Now already Segre, he looked at some topological invariant. So he looked at the number of connected components of this real locus. So the number of connected components. And then one can show that there are exactly 2 components. And this is related to the observation. Then, okay, here is you have always something positive. So then this polynomial should be positive for 0. And this number of 2 connected components are related to the sign of this one. So there's plus here. Okay. But now we want to have something smooth. So how are I going to have something smooth? So we will take another cubic form that I'm going to call psi. So I'm going to take the easiest one, just sum of cubes. This one is smooth. Okay. And that what I'm going to do, I'm going just to consider x epsilon as a cubic defined by phi plus epsilon psi equals to 0. So, and I'm going to look at this, those cubics for epsilon small enough. So then x eta is smooth. And we can use Arrhenius theorem. For epsilon small enough, x eta, the set of real points, is diffeomorphic to x0 of R, which is just the set of y of R. And the number of connected components is preserved. So in particular, we see that the P0 here of x epsilon, so the number of connected components is 2, but should be 1 for rational ones. So here we are using this invariant to show that something is not rational. Okay, so more generally, how can one establish the failure of rationality? So as in this example, classically, what one would do is you pick your variety, compute some invariant, figure out that the invariant is non-zero, and then deduce that x is not rational. So let me give some more examples. So classically, for threefolds, so we said for curves and for surfaces over C, the four notions are presented in the beginning were all equivalent. So for threefolds, there are three examples coming to 80s. So cubics, smooth cubics in P4 over C, never rational. This was done by Clemens Griffiths using intermediate Jacobian as invariant. Also, quartics in P4, this is a result by Skowski and Manin, are also never rational, and this was done using rigidity. Rigidity is related to the study of birational automorphisms. And finally, I wanted to mention an example by Artin and Mumford, where he was considering first some double cover ramified along a quartic, some particular quartic, and then Z was a resolution of Y, resolution of singularities. Then they showed that there is this topological invariant, which also equals to the Brau group, is non-trivial. So again, this is topological invariant, and the way they showed that, they established that it's non-zero is really by studying cycles very explicitly. And this invariant actually should be trivial for stably rational varieties as well, so this shows that Z is not stably rational. Also, these invariants provide examples of unirational and not rational threefolds. Well, the first example and the third example, they're unirational, and some quartics are also unirational, but we do not know for all of them. So some of them are unirational. So to summarize, so rational implies stably rational, implies unirational, rationally connected. There are unirational but not rational complex threefolds. Also, so the first implication is also strict. There are examples of stably rational, not rational complex threefolds. Again, some conic bundles constructed by Beauville, Colliot-Hélène, Sansuc, and Swinnerton d'ailleurs. So this is for varieties over complex numbers. And I also put a remark over non-closed fields. There are examples of stably rational and not rational surfaces, but the Galois group, the absolute Galois group of the base field should be quite big, and it doesn't work for finite fields. So for instance, it's still open if there is a stably rational, not rational surface over finite fields. Okay. And also, it's not known if there is an example of a rationally connected and not unirational complex variety. And this is because it's very difficult to abstract the unirationality. So to prove that something is unirational, one tries to do some explicit geometric construction, and to abstract the unirationality seems quite hard. Okay, so this is all for the classical results, and now let me talk about stable rationality more in details. So how can one show that something is stably rational? So I'd like to present an approach related to the K0 varieties. So we already had a definition of the Criterion ring of the varieties in the previous talk by Professor Kawamata. So let me briefly recall. So it's a ring with generators isomorphism classes of varieties over K. The relations is X equals to the sum of the closed and the open complement. And the ring structure is given just by the product of varieties. So how is it related to the stable rationality? So it is done by the result of Larsen and Luns. If you put L the class of a fine line, in characteristic 0, a variety, smooth projective variety is stably rational, if and only if its class is 1 in K0 mod the ideal generated by the line. So it's actually quite straightforward using weak factorization, also formulated in the previous talk. And also by Bittner's theorem, K0 varieties could be generated by the classes of smooth and projective varieties with the only relations coming from the blow-ups of smooth closed subvarieties. And so I put it because it shows that not only X is stably rational if it's equals to 1 in K0 mod L, but also K0 mod L actually parameterizes the classes of stably birational varieties over K. So how can we use this? A priori, it's difficult to compute for a given variety what would be the class in K0. But there is another application. So here is a result. An application is for the study of specialization of stable rationality, which is a result by Niquez. So he considers this field. This is a piezo series field. And little k is the field of complex numbers. Then the key point is that he constructs a specialization map from K0 varieties over big K to K0 varieties over C. And if you think a little bit about this, there is actually nothing trivial in how to construct this map, because you have to choose a special fiber for varieties over big K. And so one uses semi-algebraic sets. That's why maybe the field is so special here. And results by Khrushchevsky and Kazhdan to construct the specialization map. But once you have it, then you can deduce that if you have a stably rational variety, then its specialization is also stably rational. Just because then the class of the line goes to the class of the line by this proposed specialization map, and so being equal to 1 in this quotient ring is preserved under specialization. But it's still unknown if smooth specialization of smooth rational varieties is rational. So if I just erase stably here, then it's not known in dimensions starting from 4. And here, smooth is also important, because if I erase smooth, also one can find easily counterexamples. So for example, one can specialize a smooth and rational cubic surface to a cone over elliptic curve, which is not going to be rational, and it's a singular variety. Okay, so since we were speaking about specialization, I'm also interested in the deformation of the property of rationality. So here, by family, I just mean some deformation of some varieties, not a moduli space, but just some smooth and projective map over some based scheme, B. Based scheme is quasi-projective over C. Then, so what is this deformation problem? You fix just one point in B, and then assume, for example, that XB0 is rationally connected just for one fiber. Then one can show that all the fibers are rationally connected, just if you know that one is rationally connected. Well, now it goes back to 90s, and it uses deformation theory. So it uses some arguments. So then for rationality, you may wonder the same question. If I have one irrational fiber, what happens for other fibers? Well, for n equals to 1 and 2, we have the same property. For curves, for smooth curves, it's enough to observe that genus is constant in smooth and projective families of curves. So you have one of genus 0, then all fibers of genus 0. And for surfaces, you also have Castelnuovo-Enriquen's criterion, which states that the surface is rational if and only if you have these two cohomological invariants that vanish, and this condition is also constant in smooth families. But in higher dimensions, there is no such nice criterion of rationality, and in particular, in dimension 3, it's still unknown if rationality is deformation invariant or not. And unfortunately, I can't tell you what people expect changes. So it's unclear what to think about this problem. And in dimension 4, the rationality is not deformation invariant. So it's a joint work with Brennan, Hassett, and Yurchenko. And more precisely, so we show that there is a family of smooth and projective varieties of relative dimension 4 with two properties. You have many rational fibers, not only one, but actually many. You have density, but in the Euclidean topology, the usual complex topology. And for very general point, the fiber XB is not even stably rational. So for very general, I mean here that we can just remove some countable number of closed conditions. So you may think that here is the base scheme B, and then the X is over B. And then you have some many countable number of those closed conditions. And here you have rational fibers. But you have many remaining fibers that are not rational. Okay. So I will give the concrete examples later and also explain the method how to obtain such results. So first, I'd like to discuss the second part. So for the method, how will you show that a very general fiber is not stably rational? So this method was introduced by Claire Voisin. And well, as a description, what you want to do, you fix your favorite variety, so everybody has a definition of favorite, and then you want to show that it's not stably rational. So for example, in Artin Mumford's example, one was able to compute the Brau group, this topological invariant, and then show that then the variety is not stably rational. But unfortunately, sometimes it's not possible to compute those invariants explicitly and directly. So in the specialization, what happens is you specialize X to some eventually mildly singular variety and compute the invariant of this singular variety, show that it's non-zero, and then deduce that the X is not stably rational. It's actually what happened in the Segres example. We would specialize it to something which was mildly singular and then use this variety. Okay, so the key words here are reference varieties. So actually, in many recent results, those X0, so special varieties with non-trivial invariants, they are almost every time the same, or almost the same. So one would like to have more reference varieties. And also, the singularities are important here. So, well, some mildly singular varieties. They are not at all the same types of singularities in the minimal model program, but still, it's actually an important ingredient. So now, let me be more precise, so how this method works. First, I'll give you, so I call it translated version in a sense that, well, a priori, there are all notions which are known in this algorithm. And then I'll explain it more in details why it works. So you have this time generically smooth, so I allow some singular fibers, but the general fibers are smooth. So I have this family with quasi-projective base over C. So what you have to do, so it's an algorithm. So what you have to do is you have to find just one fiber, one point and one fiber with two conditions. So there is a resolution of singularities such that the singularities are not too bad, so the resolution property. So for any point in Y, the fiber is either one point, so this happens often because it's a resolution of singularities, or if it's not a point, it's a union of smooth rational varieties. So for example, it happens if Y has ordinary double points and singularities. And here, a point has actually quite a strong meaning. So it's not only the C point, not only the closed point, but also any scheme point we consider in this situation. So it could be a generic point of a curve, for example. So I just wanted to mention this. It's not only closed points. And the second is the abstraction condition. You have some non-trivial invariants. So for example, this topologically invariant Brauer group is non-zero. So you just find one member of this family with two properties, and then you can conclude that a very general one is not stably rational. So that's the version we're actually going to use. So you can just remember this one, but in maybe 2-3 slides, I'd like to explain what's behind. But we will still use this version later. So how are we going to realize this? So there is this invariant, the Chow group of zero cycles. So for field and the proper variety, we look at the free abelian group generated by closed points. So over C, you can just take points. And we mod out by a rational equivalence relation, where this equivalence means that basically it's generated by the fact that the divisors of functions on curves should be rational equivalent to 0. And actually, we already computed, in some cases, this invariance. So again, coming back to Sagar's example. So if we have a smooth and projective and rationally connected variety over reals with a point, then actually this group mod 2 is Z mod 2 power so the sum of some number of copies of Z mod 2, and this number of copies is the number of connected components. So actually, we already saw this example. And also for proper variety, so that's important that the variety is proper, we have a degree map, which goes to Z, and where we send an element of the Chow group, which is of this type, to some ni's, the field extension here, it's a finite field extension. And again, over complex numbers, you can forget this factor, just sum of ni's. Well, anyway, so there is this group. And so actually, this group is an invariant that we can control well under specialization. So we define that a variety X over K, a proper variety, is universally CG0 trivial if this degree map is an isomorphism for any field extension. So really any field extension, not necessarily finite, but really for any field extension. So some examples. Well, for Pn, the Chow group for zero cycles is Z. So it works. Once it works for Pn, you may think maybe for rational varieties, for stably rational varieties. So yes, it holds. But it does not necessarily hold for rationally connected varieties. So sometimes people say that, oh, what is if X is rationally connected? Indeed, we have an isomorphism induced by degree over, say, C, but not over all field extensions. Okay, so that's important here. Okay, so how can we use this universal CGO triviality, and how can we translate it differently? So some people like fills, and other people like diagonals. So I decided to present this approach as well. So the same property could be translated as this decomposition. So you have this diagonal in X cross X, which can be decomposed as a sum of two cycles, X cross some point or zero cycles of degree 1, and W is sort of small in a sense that it's included in D cross X, where D is a proper closed subset. So 1 implies 2 because you can take as a field the function field of x, as a point, generic point of x, and then a zero cycle of degree 1. Then you can consider the difference eta minus x. So this is a zero cycle of degree 0 in C0XL, so it should be 0 because it's an isomorphism. And so when you spread out it to the product of x cross x, then eta gives you diagonal, little x gives you this first summand, and w is the remaining summand. So, and for x smooth, also actually those properties are equivalent. So now I'll just say one word, why. So here is this decomposition of the diagonal that we've just had. And x, we assume that it's smooth and projective. Then, well, those cycles, they induce some action on main invariants that is called action of correspondences. So they act on Chow groups, they act on Brauer group, and on other invariants such as global sections of differential forms. And this particular integral diagonal decomposition so tells you that the action is special. So from one point of view, diagonal acts as identity because it's diagonal. And those are too small, and so this right-hand side acts as 0 for these types of invariants in particular. So that's how one can show that, well, identity equals to 0 means that the invariants are 0. So for Brauer group, for global sections of differential forms, and for the universal CHD reality. So now, with the help of this property, I can actually tell you what is behind the specialization method algorithm. So if you have a family generically smooth as before, then if you show that there is one member with those two property, resolution and abstraction, but in a better way, you assume that for any point the fiber is universally CHD or trivial, and Z, the resolution, is not universally CHD or trivial. So for example, the Brauer group is non-zero because this decomposition implies the universal triviality and the triviality of the Brauer group. So if you can show this, then again, the XB is not stably rational for a very general member of the family. Okay. So maybe just a word why we have this very general property. So where does it come from? This is because we want to study this diagonal decomposition. We want to view it as an equation where the parameters, so what is this? So it's rational equivalence of cycles, and then we have to specify W and D, so you have some parameters in Hilbert schemes and the Chow schemes. So those schemes, they have countable number of components. And then this equality is just an equality, so it defines a closed condition in some countable number of schemes. And so that's how we have here this condition. We have to remove some countable number of closed conditions. So it's very briefly what is the idea. Okay, so now let me discuss some applications. So this method, as I said, was introduced first by Claire Voisin. So she was able to show that a very general double cover of P3 ramified along a quartic with at most 7 nodes is not stably rational. So, okay, it's not stably rational within here. So as a reference variety, she used Artin-Mumford example. And in her example, the singularities are ordinary double points. So I'll explain in the next example this more in details. Of the joint work with Collier-Telen, we were considering a very general quartic threefolds. And they're not stably rational. So according to this specialization method, first we produce a family. So the family is very easy to produce here. So you just look at all quartic threefolds in P4. You just have some projective space P that parameterizes the coefficients. And then you look just at all quartic threefolds. Then we have to find some particular one. So for this, we recall this Artin-Mumford example. So we had this double cover, and then we had for resolution, the invariant is non-zero. So this one, this is not quartic, right? So there is this term of degree 2. So who can produce a quartic from this? So in order to produce, we can do something very stupid, just add a square here, right? So this is 0 square. So now this is a quartic, and it's birational to the Artin-Mumford example. So if you put z0 equals to 1, you have the same equations. So that's birational. And hence, in particular, the Brauer group is non-trivial for the resolution of our quartic. Yeah. Because Brauer group is a birational invariant for smooth and projective varieties. So in this way, we have the abstraction condition. And then we also check that the resolution condition holds. And actually, we have to construct the resolution of singularities. And this is more complicated than just the ordinary double point singularities. So there are some lines that we have to blow up, and also double points. So it's not that hard, but still, it's more general. OK, so some other applications. Tataro was also considering hypersurfaces of sufficiently high degree here. He showed that they are not stably rational. And as reference varieties, he considered something different. So he considered cyclic covers and characteristic 2. So Kohler actually considered those types of cyclic covers also in the 90s. And so what he showed that sometimes there are global sections of differential forms. And so this is the invariant that Tataro used. And in his case, the singularities are also ordinary double points. So there are also many other applications. So in particular, in dimension 3, so Hassett and Chinkel, they were able to show that almost everything is not stably rational. So if you consider some Fanos threefolds, so then you have classification according to some invariants. And so if you pick Fanos threefolds that are not rational, you know that they're not rational, and not birational to cubic threefold. Then for those Fanos threefolds, they are not stably rational. And the case of cubic threefolds is actually still open. I'll mention this at the end. Then there are more applications. I put some names, Bouville, Okada, but there are more. OK. So now, because we were using these reference varieties, the Artin-Mumford example, all those cyclic covers, then you may wonder, OK, it would be good to produce more reference varieties. And for example, compute this topological invariant Brauer group for more classes of varieties. And actually, there are explicit formulas for this invariant in some cases. So for example, for fibrations in conics by Collier-Tolan, and for fibrations of a P2 in quadric surfaces. So this invariant could be also computed by completely algebraic tools, such as Galois cohomology. And so that's how these formulas are obtained. And they are in terms of sort of combinatorics of the discriminant divisor. So let me give you one example that we are going to use. That's why I'm giving it. So you consider Y, so fibration in quadric surfaces over P2, which we also view inside P2 cross P3. And here is the equation. So for fibration in quadrics, I have S, T, U, and V as variables of quadrics. So with just a diagonal quadratic form. And so F is a conic, and then I have those coefficients. And the fibration is just the first projection map. OK, so let me draw a picture. So here is P2. And so what is discriminant divisor? So discriminant divisor, where the quadric drops the rank, is xyz squared times f. So it's just the product of the coefficients of my quadratic form. So how does this look like? It looks like a triangle with actually double sides. So double sides. And a conic inside. Okay? So this is a discriminant locus here. And so this particular, so this is sort of combinatorial objects, that's why I draw it. And one can show that there is some non-trivial element in the Brauer group. So I'm not going to explain how to okay, I can do it also like this, how to consider what is this element, but anyways, there is one non-trivial element. And also note that here, Y, we can also view it as the hypersurface in P2 cross P3 with by degree 2, 2. So 2 in YXZ and 2 in STUV. Okay. So now I'm ready to come back to this non-deformation invariance for the rationality. So here is the result I mentioned. And then the concrete example says follows. So first, you can consider the family of hypersurfaces, smooth hypersurfaces of by degree 2, 2, as we just considered before, just in the previous slide. And so you consider as B just the parameter space for the coefficients of smooth 2, 2 hypersurfaces. So the coefficients are parameterized by P59, and so you just take an open corresponding to smooth ones. So this was our original example. And recently, we found one more natural or easier somehow. You just take the smooth intersections of 3 quadrics in P7. So this also gives you four folds, and it also works. So let me first explain how to show that the very general member of those families is not stably rational. So in these examples, we are going to use the specialization method for this property. So we almost did everything. So we're just going to use this variety Y for 1. So this is by degree hypersurface of degree 2, 2. And I mentioned already that because the Brau group is non-trivial, we have obstruction. And we also have the resolution property. We can do it explicitly. And so the singularities of the following shape. So this is my Y over P2. And so I have a singularities conic over each line. And over each tangency point, I also have conic. So that's a singular locus inside of Y. And well, by some number of blowing ups, one can show that the resolution property also holds. So, well, the reason I showed this to you is to give you an idea of what types of singularities we actually appear here. And it's always a painful step in the method because it takes lots of time to construct those resolutions. And, well, we learn nothing with this, just keep computing things. So, well, it would be great to somehow classify the singularities, so like understand it better. So for the second examples of the intersections of 3 quadrics, one can also use this Y as reference variety. So in some way. So this is for the part I, the 2I. And then let's see how can one show that we have density of rational fibers. So I'll do it for the example of the intersections of 3 quadrics. First, actually, we don't want to look at the intersection of 3 quadrics, but rather fibration quadric surfaces. Bouville showed that any such intersection is birational to fibration quadric surfaces that I call Q of X to P2. Then, similarly to the first example, X is rational if the fibration P has a rational section. This corresponds to the fact that the quadric is rational as soon as it has a point. And also, we can do even better. It's enough to assume that it has a multi-section intersecting fibers in odd degree. And this is connected to the Springer's theorem that a quadric has a point as soon as it has a point in an extension of odd degree. So that's enough. And then we don't want to look for some sections inside X, but rather by some Hodge classes. And here this method works because the integral Hodge conjecture holds in this case. So actually, instead of considering some multi-sections, it's enough to find integral Hodge classes intersecting fibers in odd degree. So that's how our problem now is to study some particular Hodge classes, also for the variation of the Hodge structure in my family. Okay, so then, well, I want to find many rational fibers. So let's already try find at least one. So one can find one which is birational to quadric bundle with a section. So now I just want to show you what it looks like. So it's like this. After the talk, if you want, we can show you where is the section, where is it hidden. But well, I mean, you can just really find explicit examples with sections. And once you have one, you want to look at the variation of this Hodge structure. So first you observe that, okay, you have this Hodge diamond, and so it's of degree weight 2, so the middle cohomology is of degree 2, of weight 2. And this allows to use some density criterion. So what happens is that, well, you have one fiber with a section, but then if in the family the Hodge structure varies, and then you want to catch some particular classes that have odd intersections with fibers. So there is a criterion, so in terms of some infinitesimal period map. So what you do, you have to find just one point in B and one element here, and to compute this infinitesimal period map, which goes to this group, such that this map evaluated at gamma is surjective. So one can find this in the book by Claire Vazin. And let me show you that how we apply it in this particular situation. So it's actually very well known how to compute those period maps in the case of, say, complete intersections of some quadrics or just hypersurfaces. So in the following way. So here is my intersection of 3 quadrics, and then I fix their equations. Then I form one polynomial, just the sum, in this ring. And then I consider the ideal generated by all partial derivatives of this polynomial. Of course, the first 3 are just going to give Q0, Q1, and Q2, and then I have other partial derivatives. And then I form the quotient ring. So it's a quotient ring. It's a graded ring with respect to mu and x. And I consider the elements of graded degree AB. Then Terrasoma showed that actually this primitive cohomology, so modular what comes from the projective space, is just expressed as this graded part. And the map we're interested in, the infinitesimal period map, is identified with multiplication. So it's really easy. You just have this like very explicit polynomial ring, and then you just have multiplication on some graded pieces. And then you can find example when it's a surjective with Macaulay. So what you do to find this example, you actually look at this one. You say, oh, I already wrote those formulas. I don't need to type it again. And so it doesn't work for this particular intersection of 3 quadrics. But if you add here some small coefficients, some such as, I don't know, maybe x5, x6, or something like this, you just add some little number of terms. And then you have this surjectivity criterion that could be verified, for instance, with Macaulay. So this shows that the density of rational fibers by this criterion due to Claire Vazin. So, okay, what remains? So open questions to finish. Cubics, all still not understood. So cubic threefolds by Clemenson-Griffiths result, they are never rational. But the stable rationality is still not known. And actually, it doesn't look like this universal C0 triviality property is going to help, because Claire Vazin was able to show that some, and actually many, cubic threefolds are universally C0 trivial. So this invariant is not going to help. And also for cubic fourfolds, so well, it's known that there are families of rational cubic fourfolds, so started by a work of Hassett. And very general is expected not to be rational, but it's supposed to be very difficult, widely open program. Okay, so thank you for your attention.